Hello viewers, welcome back. In previous lecture we had discussed the first come first serve scheduling algorithm and we have seen some of the problems also. In this lecture we will understand the shortest job first scheduling algorithm. A different approach to CPU scheduling is the shortest job first scheduling algorithm, and this algorithm is associated with each process the length of the process next CPU burst. Means, as per the name, shortest job first scheduling algorithm. So always it prefers the length of the process, the next CPU burst. Means whichever the process is having the smallest in the length, so that process is going to be executed by the CPU, or CPU will occupy that process, or process occupies the CPU. The meaning is same, right? So CPU will be available for that process whose length is the smallest in the next CPU burst. So when the CPU is available, it is assigned to the process that has the smallest next CPU burst. Means in the ready queue, whichever the process is having the smallest next CPU burst, so that process will be assigned to the CPU. If assume that the next CPU burst of the two processes are the same, then we apply the first come first serve scheduling algorithm, and with the help of this scheduling algorithm we can break the tie between the two processes. So whichever the process enters the first will serve first, and whichever enters next will serve next in the shortest job first scheduling algorithm. Now this shortest job first can be either primitive or non-primitive. A more appropriate term for this scheduling method would be the shortest next CPU burst algorithm. So we can call it as shortest next CPU burst algorithm because this algorithm finds the shortest next process which having the less or the shortest CPU burst. So that process occupies the CPU. So therefore we call it as shortest next CPU burst algorithm, because scheduling depend on the length of the next CPU burst of the process rather than its total length. So we are not calculating the total length, we are just depend on the length of the next CPU burst of a process. So therefore it is called shortest job first scheduling algorithm. So whichever the process is having a shortest burst time will get the CPU first. So let us understand both these non-primitive and primitive scheduling shortest job first scheduling algorithm by these examples. Now consider the following set of processes with the length of the CPU burst given in the millisecond. Now as per this table, the P1 has 6 millisecond, P2 has 8 millisecond, P3 has 7 millisecond and P4 has 3 millisecond. Now as per this table, the shortest one is the P4. The first shortest one is the P4, means the CPU if available, so it will be available for P1 first. Then next it will find which is the next smallest CPU burst time. So next is the P2, right? After P2, next smallest CPU burst time will be of P3, and final or the fourth will be the P2. So based on this table we will prepare the Gantt chart, right? So we prepare the Gantt chart with the timeline. So as per the timeline, so 0th timeline, the P4 enters the CPU, it completes its burst time, that is 3 burst time. So it will complete and it will exit at this point, and in this point, so the P1 gets enter, right? It has the total 6 millisecond of burst time, so it will complete 6 millisecond burst time and it will exit at this point. At the time the P1 get exit, one more process, the next shortest CPU burst time enters the CPU, that is P3, and it has 7 millisecond. So it will execute for 7 millisecond and it will exit at 16th millisecond, and one more process, that is P2, occupies the CPU at 16th millisecond and it completes its execution. Total CPU burst time is 8 millisecond. So 16 plus 8, 24. At the 24th millisecond, the P2 get exit from the CPU. So this is how you can prepare the Gantt chart. First understand the burst time, then you need to find the shortest or the smallest one among these four. So the smallest has to be first assigned to the Gantt chart and it should complete its burst time, and then you can go for the next shortest CPU burst time process. Now if we are using the first come first serve scheduling algorithm scheme, the average waiting time would be 10.25 millisecond for these processes. But we are using a shortest job first scheduling algorithm and it is non-primitive, right? Non-primitive means we are not checking at what time these processes has entered. We are thinking that all the processes entered at a time, right? So based on the shortest CPU burst time, so we are preparing this Gantt chart and we are calculating the rest of the things like waiting time of P1 process. So how much time it is waiting? It is waiting till this point, means this point it is entering, the P1 is entering, means it has waited for 3 millisecond. So 3 millisecond would be waiting time for P1. Similarly, P2 is waiting for 16 millisecond. Now you can see the entry of the P2 taken place here. So 16th millisecond the P2 has entered, means it has waited from 0 to 16, means the 16 millisecond is the waiting time of P2. Similarly, P3 entered at 9 millisecond, so it has waited from 0 to 9, means we are thinking that all processes entered at the same time. So based on this algorithm, so we are executing and preparing this Gantt chart. So P3 has waited for 9 millisecond and P4 has not waited for anything, means it has not waited, so it is just waited for 0 millisecond. So 0 would be the waiting time for the P4 because P4 is the shortest CPU burst time process, hence it occupied the CPU first. Okay, so based on these values we are calculating the average waiting time. So average waiting time, we have to add 3 plus 16 plus 9 plus 0, right? So 3 plus 16 is 19, 19 plus 9 is 28. So 28 is divided by 4, that is 7 millisecond. So as per first come first serve scheduling algorithm, 10.25 millisecond, and as per this shortest job first scheduling, that is 7 millisecond, right? So it is non-primitive. Let us go to the next example and let us understand the next example. So this is the shortest job first scheduling primitive example. Now again consider a table. So based on this table you should prepare the Gantt chart, and this Gantt chart, again the same terminology we have to adapt for preparing the Gantt chart. We have to first of all understand the shortest one. So which one is the shortest in this table? The P2 is the shortest one. So this one is the shortest one. The next smallest CPU burst time is P4, that is the 5 burst time, this one. The next smallest CPU burst time is P1, this one, and the next is this one, P3. But in primitive, if we are having shortest job first scheduling algorithm, and we are using the primitive method, and there is a arrival time of each process. So even though smallest CPU burst time is the P2 process, but P2 has not arrived at 0 millisecond, it has arrived 1 millisecond, right? So we could not make the CPUs to sit idle. So at 0th millisecond the P1 is entered, means it arrived. So hence we assign the CPU burst time to P1. So total it need to have 8 millisecond of burst time, but we are not assigning 8 millisecond of time to P1, because next very next millisecond the next process P2 is arriving, which having the smallest burst time compared to the P1. So how we can prepare the Gantt chart? Let us understand this Gantt chart, and this is the a timeline of this Gantt chart. Now at 0th millisecond, right, so P1 gets entry and it will execute till the 1 millisecond. So after 1 millisecond, right, so it is preempted, right? So P1 is preempted because P1 is having a total burst time is 8 millisecond and P2 is having 4 millisecond. So we have to choose the shortest one. So shortest is the P2. So P2 will occupy the CPU. So P2 entry point is 1 millisecond. So at this point of time, so it is taking entry, right? So it is completing it 4 millisecond of execution, right? So 4 plus 1, so 5th millisecond, so it is getting exit, right? So it completes its task and it will come out from the CPU. Now we are finding the next shortest one. The P4 is the next shortest CPU burst time holder, right? So it will occupy the CPU, right? And it will burst for 5 millisecond. So 5 plus 5, that is 10. So at the 10th millisecond it will exit, right? And after this, which one is the smallest? The P1 is the smallest. Already we have given 1 millisecond, right? So already 8 minus 1, so it has a 7 millisecond of time. Now we are giving this CPU, right, at the 10th millisecond to P1. It will burst for 7 millisecond, exit at 17th millisecond. At the 17th millisecond, one more process P3 will occupy the CPU, right? And the total burst time of this P3 is 9 millisecond. So it will burst for 9 milliseconds. 17 plus 9 is 26. So at the 26th millisecond, the P3 will exit from the CPU. So this is how you can prepare the Gantt chart. So these kinds of question might be asked in your competitive exams like net, set, gate, right? So you have to prepare Gantt chart in this fashion. So based on their arrival time, we have to choose the smallest one and we have to prepare this Gantt chart. So if we prepare this Gantt chart, then only we can calculate the waiting time. So waiting time is calculated based on this formula. So total waiting time minus number of millisecond process executed. Now right now the P1 has already executed 1 millisecond. So total waiting time minus number of millisecond process executed minus its arrival time. So this is the formula. Okay. Now if we are using non-preemptive, means in previous example, as per previous example, if the same processes and same amount of burst time, if we are using, the result of the non-primitive shortest job first algorithm is 7.75 millisecond. Now let us calculate as per this Gantt chart and let us find out what would be the result. What is the waiting time? Now P1 is waiting for 9 milliseconds. So how we can calculate? So where is the P1? So P1 is arriving here, 0th millisecond, right? 0th millisecond, that is the arrival time. So this is the 0, right? So what is the 10? So 10 is the number of, total waiting time. So total waiting time is 10. So you can see next time it is entering at 10 milliseconds. So this is the total waiting time of P1, right? So 10 minus 1. So this 1 is already, it has occupied the CPU for 1 millisecond, and it is processed for 1 millisecond. So number of millisecond process executed, that is 1, right? So based on this formula, the waiting time we can find out for P1 is 9 millisecond. Similarly for P2, right? So P2, that is the total waiting time, 1 millisecond it is waiting. So next it is entering the CPU after 1 millisecond, right? And number of millisecond process executed. So it is completed all its burst CPU burst time at a time. So hence we are not calculating. So it is keeping as 0, right? Arrival time is 1. So total waiting time is 0. See, when the P2 is entering, right? So its arrival time is 1, right? Arrival time is 1 millisecond. So immediately it is occupying the CPU. So hence it is not waiting for a single millisecond. So therefore the waiting time is calculated in this fashion, right? So total waiting time minus number of millisecond process executed minus arrival time. So earlier it has not executed. So therefore we are keeping 0 value for this number of millisecond process executed. Okay, hope you understood this one. Coming to P3, it is waiting, total waiting time is 17 milliseconds. So it is taking entry at 17th millisecond. So total waiting time for P3 process is 17 minus 0, because before this it has not executed. So CPU has not allocated. So hence number of millisecond process executed is 0. So 2 is the arrival time. When did it arrived? So arrival time is 2 millisecond. So 17 minus 0 minus 2, that is 15 millisecond is the waiting time of the P3, right? So as per the Gantt chart, it is a 17 millisecond, but it has not arrived at 0 millisecond. It has arrived at 2 millisecond. So this millisecond has to be minus into 17. So 17 minus 2 is 15, right? In this fashion also we can calculate the waiting time of the process. Now P4, so total waiting time is 5. So it is taking entry at the 5th millisecond, right? So burst time is 0, means number of millisecond process executed is 0. So 3 is the arrival time. So arrival time is 3. So 5 minus 3 is 2 millisecond. It is waiting for only 2 millisecond, right? So as per this, if we calculate the average waiting time, so 9 plus 0 plus 15 is 9 plus 15 is 24. 24 plus 2 is 26. So 26 divided by 4, right? That is 6.5 millisecond in primitive, right? In non-primitive SJF scheduling, 7.75 millisecond. So this is how we can calculate this shortest job first scheduling algorithm, primitive as well as non-primitive. Now the problem with the shortest job first scheduling algorithm is, the real difficulty of this algorithm is knowing the length of the next CPU burst. So after all, we should know the shortest job, means we have to know the length of the next CPU burst, that is the real difficulty in the shortest job first algorithm. Although SJF algorithm is optimal, it cannot be implemented at the level of short-term CPU scheduling. There is no way to know the length of the next CPU burst. So one approach is, these are all the problems what we have in the shortest job first scheduling algorithm. So to try a approximate shortest job first scheduling, right, we may not know the length of the next CPU burst, but we may be able to predict its value. So based on its value, we can occupy or we can allocate the CPU to that smallest next CPU burst time process. We expect that the next CPU burst will be the similar in the length of the previous one. So these are all the approaches what we are having. So thus, by computing an approximation of the length of the next CPU burst, we can pick the process with the shortest predicted CPU burst. So as we have already seen in the example, so based on the shortest CPU burst time, we can predict. So approximation of the length of the next CPU burst, we can pick the process with the shortest predicted CPU burst time, and we can assign the CPU to that process. So hope you understood this concept. So this is the second scheduling algorithm. After the first come first serve scheduling algorithm, shortest job first scheduling algorithm is the second one. So we will come up with the example in the next lecture on shortest job first scheduling algorithm. So thank you for watching.